Hi and welcome to High School Physics Explained, and I'm going to go through the answers of the HSC exam for 2019. But unlike past exams where I have gone through the whole exam with the answers, this time I'm going to create 4 smaller videos where I'm going to just break them up into the 4 modules. So Module 5, which is Advanced Mechanics, Module 6, Electromagnetism, Module 7, which is the nature of light, and lastly Module 8, which is the universe to the atom. In this particular video I'm going to concentrate on the Advanced Mechanics section, so Module 5. Now the reason I do that is so that you, as you go finish each of the modules throughout the year, you can review some questions dealing just with the module that you're studying. If you're not actually part of the Australian curriculum or New South Wales curriculum here, there's still lots of benefits by watching these videos because physics is still physics, so by all means watch and check out the questions. We're dealing basically with projectile motion, circular motion, and in gravity. So let's get started. I encourage you, any of these videos, that you pause the video at the question phase. Try the question before you listen to the answer. This is question number 1, the easiest question in the paper, supposedly. So here about a projectile launch at a cannon, and you're asked which response shows you the arrow that represents the velocity of projectile at its maximum height. Well, if you know that projectile motion, we have this classic parabola, and that is because we have a constant velocity in that direction and we have a changing velocity in that direction. At the top here, the velocity vertically is 0, so all we have left is the horizontal component, and therefore D is the correct answer. Question number 9, we have 2 satellites that have the same mass. One is a LEO. LEO stands for low Earth orbit, and then what we have is also another one, a GEO, which stands for a geostationary Earth orbit. And so we're basically told that the total energy of the satellite is half of its gravitational potential energy. So straight away we can say, well, since gravitational potential energy is negative g m little m over r, then the total energy is going to be negative g capital M little m over 2r. We're asked now to find which of these responses is correct for identifying which has the greatest orbital period and which has the greatest total energy. Now, if this is my planet over here and I have a satellite in this orbit and a satellite in this orbit, my orbital period basically increases as we go out based on Kepler's third law. R cubed over t squared is a constant, so therefore the orbital period that has the greatest period is our GEO. We're then asked which has the greatest total energy. Well, since this is negative, as we go further and further away, this gets closer and closer and closer to 0 as R becomes infinite. So we're actually increasing the total energy as we move away. So therefore the total energy is greater for the GEO. So therefore D is our only correct answer. Question 11, a dwarf planet orbits the Sun with a period of 40,000 years. The average distance from the Sun to Earth is 1 astronomical unit. What is the average distance between this dwarf planet and the Sun in astronomical units? So this is again a Kepler's third law problem, which says that r cubed over t squared is going to be the same value for any other object orbiting a common structure, so in this case orbiting our Sun. So this is going to be our dwarf planet, this is going to be our Earth. So if we substitute everything that we need and also the things we're looking for, we know that the dwarf planet's radius is what we're looking for, so we're going to put r cubed there. Its period in this case is 40,000 years, and the Earth's radius we know is 1 astronomical unit, and in this case our period is not 40,000 years, it's 1 year. So now that makes it really obvious that r cubed is equal to 40,000, so the cube root of 40,000 is what our r is going to be required, and that means our total answer is the cube root of 40,000, which is C. Question number 14, now we have a satellite in a circular orbit at a distance of r from the centre of Earth and it has an orbital velocity v. If the distance was increased to 2r, what would be the satellite's orbital velocity? Well, if we equate the gravitational formula with the centripetal formula, we're going to get our orbital velocity formula, which is v is equal to the square root of gm over r. Now, we are increasing the distance here by 2r, so therefore the new one, and I'm going to call this just v dash, is going to be the square root of gm over 2r. Now, if I take this 2 outside, I have to take out 1 over the square root of 2 to have the square root of gm over r by itself. So now you see that this is my original velocity. My new velocity is now 1 over root 2, and if you work that out, that becomes b. Let's have a look at question 20. An apparatus shown. We have a backboard that is connected by a rod to a shaft, and this shaft is spun by an electric motor, so it's going to go in a circle in a horizontal plane. And we have a cube that is suspended by the string so it touches the surface of the backboard. Then we're told that when the angular velocity of the motor is great enough, the string is cut. And then, surprise, surprise, the cube doesn't move, it stays put. So it's important that we analyze this picture before we even look at the question. And that question being is really which of these statements adequately describes the forces in this situation. So we're going to pull this apart. And there's a little tip with an exam, is that before you look at your responses that you have to choose from, is that you really have a good understanding of the physics that's going on here. Now, the fact that this is spinning means that this block is experiencing a normal force towards the center. So this normal force is the centripetal force. We're getting a cut here on the string, and because it's not sliding down, we have two forces at play in the vertical plane. We have the force of mg acting down and the force of friction acting up. And that friction, of course, is equal to mu n, where n is the normal. Now that normal is this normal here, which is the force pushing it in towards the center. So now that we have a good understanding of the situation, let's have a look at the responses and see if we can find out which is the best statement. The statement for A says the sum of the forces on the cube is 0. Now, if the sum of the forces of the cube is 0, that means we have a net force, basically, equal to 0, which means, therefore, there is no acceleration. But there is acceleration here. It's going in a circle. We have centripetal force acting inwards, which means the object is not staying in a linear path. It's constantly changing its velocity. So therefore, since it is accelerating, we cannot argue that the sum of the forces on the cube is 0. So A is incorrect. B, the horizontal force of the backboard on the cube is equal to the magnitude of the horizontal force of the cube on the backboard. Let's pull that up and make it really clear. We're saying that the force of the backboard on the cube is equal in magnitude of the force of the cube on the backboard. If you look very careful, this is Newton's third law. Force of A on B equals force of B on A. And that is always true. So therefore, B is correct. Therefore, we have to look at C and D just to be sure that B is correct, and see why C and D are wrong. C says the horizontal force of the backboard on the cube is greater than the horizontal force of the cube on the backboard. In other words, it's saying this is not true. But it actually adds a rider here, resulting in a net centripetal force. And there is a fundamental flaw in this argument. You see, to get a net force, and that of course means you have sum of forces acting, it's important to understand that the forces acting for a net force must be all acting on the one object. And this is the force of the backboard on the cube, and this one is the force of the cube on the backboard. These do not cancel out, resulting in a net force. So therefore, this is incorrect. Finally, response D, the force of friction between the cube and the backboard is independent of the force of the backboard on the cube because these forces are perpendicular to each other. Well, that's not true because the force of friction we've established here is dependent on the normal, and the normal is the centripetal force. See why it's important to annotate this. This makes it really clear that the force of the backboard on the cube, that's the normal, right, contributes to the value for the friction force. So therefore D is incorrect. So now let's have a look at our short answer questions, and we're now jumping straight to question 26. And we're going to go through it and look at how we might respond to this question. It's worth 6 marks, so you should be thinking about 9 minutes to do this question. A student carried out an experiment to investigate the relationship between torque produced by force and the angle at which the force is applied. We're going to get a 400 Newton force is applied, and then what we're going to see is we're going to measure the torque as we change the angle. So the student here has graphed data of the angle changing in terms of the force. Now before I go on, this is a torque question, and so therefore you definitely need to know a little bit about torque, but it is also about the understanding of the nature of modeling and how we justify our models based on experimental data. So this student has graphed the results and has gotten here a lovely line of best fit, which is going to start at 0, because we're going to say that the torque is equal to 0 when the force is 0, and we've got a lovely linear fit. And the student says this is the relationship. Now we're not arguing here that this is the correct relationship, but this is what the student is arguing. And we are now asked to justify the validity of the student's model. So based on the data, we can argue that the validity is good because we have a linear relationship, and the fact that we have a relationship of torque equals some k multiplied by theta, this is a linear relationship. So there's one justification for why you would say this is valid. We have data that is linear, and so this mathematics supports that. But there's another reason why we can justify it. If you were to work out the slope of this graph, and again you would need to make sure that you are measuring not from the dot points here, but measuring from the actual line of best fit that you've got on there, you're going to get a value for the slope of equaling approximately 1.7, and that of course is rise over run, so Newton meters per degree. And so we have 2 reasons why we can argue that this is valid. We have a linear relationship, which is right there, and we can determine the slope of this line, and that slope is consistent to what the student thinks it is. So that's a justification. Now going on to B, the question is justify answer with reference to different model. Well, number 1, the model here is incorrect, because if you look at the formulas, torque is equal to the force multiplied by the sine of theta. And if we were to graph this in terms of torque and angle over here, then what you're going to get is you're going to get a curve that looks like this. And that displays the sine relationship. So that's the correct model. But that doesn't answer the question as to why this is wrong. And the key here is that the student chose angles that are too small. In other words, if he just looked at, let's say that was 0 over here, and this was our 25 over here, you see that we have roughly a linear fit. His range of data was too small. He should have extended this on to, let's say, 90 degrees. And had he gone on to 90 degrees, he would have found that this actually does start to curve across like so. So, answering the question, what happens? Well, it becomes less accurate because the fact is that his angles are too small. As the angles increase, the accuracy decreases. Had they chosen a relationship of f sine theta, had they chosen a large range of angles, that would have made the experiment valid and given the correct relationship. Question number 30. And now we have a question where we have a ball going down a ramp and then off the edge of the ramp. Now this ball travels along a frictionless track, so this ball is actually sliding down and not rolling down, so we don't have to worry about rotational dynamics here. At the instant the ball leaves the track at Q, it has a velocity of 1.5 meters per second at an angle of 50 degrees to the horizontal. So looking at this question, the first thing you should do is always label your diagram with all the data. So I'm going to actually put that in here. We know it's going to come off here at some sort of velocity, which we know is equal to 1.5, and we know that the angle here is going to be equal to 50 degrees. And so the first question we ask is calculate the difference in height between P and Q. Well, the ball has dropped a certain displacement vertically. So to determine the height, we need to look at energy. So we know that the potential energy here is going to be dropping as it goes down, but that's going to result in an increase in kinetic energy. And that's our key. Our U is going to be equal to negative K, or the other way around. So with that in mind, we ask ourselves, what do we know? What don't we know? Well, that means we have mgh, or the drop of potential energy, negative, is going to be equal to the increase in kinetic energy, which is a half mv squared. You'll see now that mass being common on both sides of the equation now can be removed. So this mathematics is independent of the mass, and so the fact that we haven't been given mass is neither here or there. We are asked, of course, to calculate the height, so we might as well just take that g value and put it onto the other side of the equation. So what you get is equal to h is equal to v squared over g times 2. Now when you substitute that in, you're going to get 1.5 squared over 2 multiplied by 9.8, and that will give us an answer of 0.1145 meters. So the second part of the question, we have a ball now falling 0.5 seconds to reach the floor, and we asked to calculate the height above Q. Well, like any projectile motion, I encourage my students to always write down all the data that you know and don't know. So I'm going to put suvat there. S, of course, is our displacement. We are needing to find it, so I'm going to put a variable s there. Our u is our initial velocity, and that is 1.5 multiplied by the sine of the angle, which is 50, and I'm going to get a value here of 1.15 meters per second. Now it's negative because I'm going to make downward my negative direction. My final velocity I'm not asked for and I don't have, so I'm going to leave it blank, and a, of course, is negative 9.8 meters per second squared, and our time is 0.5 seconds. We now see that the formula that we need to use to solve for s is equal to ut plus a half at squared. There's another thing I encourage you to do. Write down the data, write down the formula, and now substitute into the formula. That is, if you don't do any of the setting out, chances are you'll get 0 if you get it wrong. But if you do all of this here and you get the final answer wrong because you've made a little mistake along the way, you may get partial marks. Now, our u, of course, is negative 1.15 multiplied by 0.5 plus a half by 9.8 negative and 0.5 squared, and you're going to get a final answer of 1.8 meters is the height. Question 35. The apparatus shown is attached horizontally to the roof inside the car. The plane of the protractor is perpendicular to the sides of the car. Let's make sure we really got this clear. So here's my car, like so. And there's my wheels. You can see I can draw really nicely of my car. And this here is sitting across this way, like so. The car was then driven at a constant speed v on a horizontal surface, causing the string to swing to the right and remain at a constant angle theta with respect to the vertical. So what we're getting here, and I'm going to use a different color pen, is that this is swinging like so. Now, it says it's on a flat surface, so the car is not accelerating in a linear fashion. Secondly, it's sitting on a horizontal surface. This is not a banked curve type situation. This car is simply going around a circular path. That's why it's swinging out. Now it says describe how the apparatus can be used to determine the features of the car's motion, and in your answer derive an expression that relates the features of the car's motion to the angle theta. Well, this car is definitely going around a circle, so the car could be, let's say, heading in this direction, but of course it's going around in a circle like so. Because of the inertia of the object, it's going to swing out. That is, it's going to swing out that is representative of the centripetal forces at play acting on the car, and the ball will swing out. So in order to work out the mathematics of that, we need to make sure we have an understanding of the physics involved on the ball. Now the ball has experiencing, in this case, if it's at an angle here, has experiencing of a force in the downward direction, which is going to be its mg, its weight. It also has a tension or force going in that direction. Those two vectors result in the centripetal force heading in that direction. That's going to be mv squared over r. In other words, this vector plus this vector will give us the centripetal force vector. So now that I've got that relationship, we can now also include the angle here, because this angle here allows us to see that there's a relationship between this value and this value in relation to the angle. So if you look carefully, and I make this as I'll use my highlighter here, if I were to draw a lovely triangle here, like so, where this here is our centripetal force, and this here is this vector moved over here, which is our mg, you now see that the tan of theta is equal to the opposite over adjacent, and the opposite is mv squared over r, over the adjacent, which is mg. I can see that m is in common, so I can cancel that out. That leaves me with the value of v squared over gr. And that, of course, is tan theta. If I rearrange that looking at the features of the car's motion, we're interested in v, I'm going to make v my subject here. So v squared now becomes gr tan theta. And finally, I can square root both sides, and I get the square root of gr tan theta. And now I have derived an expression that relates a feature of the car's motion, in this case its velocity, to the angle. And there it is, there's the formula. So that is your final answer. In order to get full marks, it's not just giving this formula, it's understanding that it's going around in a circle at a particular radius. You need to talk about that. It's traveling at a constant speed, and you need to correctly derive this formula from our understanding, in this case, of just using the tan theta of this vector diagram that I have here. So that's question number 35. So that was the solutions to the advanced mechanics section of the HSC paper. Stay tuned, I'm going to be also doing a video on electromagnetism, of course, next, followed also by nature of light and the universe to the atom. So stay tuned. I'm Paul from High School Physics Explained. Bye for now.